Let's investigate the relationship between electric potential and the electric field. So let's start with the formula for the potential difference from B to A. And that's just equal to VB minus VA. And we'll put up a point here, point A, point B. And if I take a look at the relationship with the electric field, it's the negative of the integral from A to B of the electric field dot dl. And that's just equal to the negative of the electric field, the magnitude, times the integral from A to B dl. Now this is assuming a constant electric field. So we have an electric field here. And evaluating the differential, the integral, which is just dl, so it's just the length, that's going to be the electric field strength times the length at B minus the length at A. And that's just equal to the negative, the electric field, times the distance between B and A. Now let's take a look at a sphere. We have an electric field going out from the center. And now let's make this a hollow sphere. So we know there's no electrical lines, electrical field inside the sphere. It's only outside. So we'll look at this point we'll call A, or RA, and this point RB. So our electric field is equal to Q divided by 4 pi epsilon naught R squared. Now let's put that into our integral. VBA is equal to the negative of the integral A to B, the electric field times the differential length, and that's just the integral from A to B, put in our electric field, and our differential length, well, that's just along the radius, so we'll call that dr. And now I need to evaluate this integral. Well, I can bring out the constants. Q 4 pi epsilon naught integral, oh, I need the negative sign there, sorry. And I forgot the negative sign here. So that's A from A to B of dr over r squared. And that's just equal to, well, this q over 4 pi epsilon naught to negative. And then I'm going to have the resultant negative 1 over r from A to B. And putting in my integral, or my limits, I can take the negative out, so I'm going to have q over 4 pi epsilon naught times 1 over RB minus 1 over RA. So for R greater than R naught, if I make my potential at point B equals 0 at RB equal to infinity, then that's going to make my potential equal to q over 4 pi epsilon naught r. And if r is less than r naught, then my potential is going to equal whatever I have at the surface. So let's graph this. So if I have my electric field at R naught, the graph is going to be 0. Let's put it in red here. The graph is going to be 0 until R naught, and then it's going to be discontinuous up to some value, and then reduce down in a relationship of 1 over r squared. For the potential, well, it's going to be a little bit different, because at R naught, I don't have 0 potential. I have some constant potential, and then it reduces down for 1 over r. So this is the relationship between the electric field and the potential.